Alright, today is the last day to make my habit permanent, and unfortunately the Leetcode problem is a little bit different with all the Leetcode problem that we have solved in the past. So let's deep dive into what is the problem meaning. So the Leetcode problem is a block placement query. So we have axis and one line which have an infinite number of lines. So that could go from positive integer 1 to at the end of the infinite, and with the origin at the 0. So that means the line starts from the integer 0. So it's tending toward the positive x-axis. So that could go all the way to positive integer, but we don't know what is the length or what it could be. We are given a two-dimensional array query which contains a two types of query. So for the type of query of the type 1, so which is, you can see like here is mentioned like 1, that means that query 1, we have to build an obstacle at the distance of x. So we have to put the one obstacle at the index of x. Let's call like query of index 0, which is 1, 2. That means it's a query type 1, and we have to put the obstacle at the index 2. So there we put the obstacle at index 2 in here, and it guarantees that there's no obstacle at distance x when the query is s. So we can confirm that there will be no duplication of the obstacle across the problem. So let's move on to the query 2. For the query 2, we have given the three values in array. Start with the index 0, which is a 2. That means we are given a query type 2, and we have to check it is possible to place a block of size, which is a sz. So in here, this is a size of 3, and anywhere in the range of 0 to 3. So 0 to x means 3 in our index 1 hexamer. And in one line, such that the block entirely lines on the range of 0 or x. A block cannot be placed if it's intersect with any obstacle, but it may touch it. So we do not actually place the block. So we're just trying to visualize it, and the queries are separate. So we have to return a Boolean array result where result of each index is true if we can place the block of specific in the index query for the type 2, and a false if otherwise. So let's go through the example 1. So if we go through it, we can see the only type 1 of the query, only 1, and there's a 3. So we have to return the 3 output array in here. So let's check the example 2. We have 2 types of obstacle and then 3 types of blocking the placement. And that means we have to return the 3 type of Boolean in here. So let's try to understand the example 1 first instead of moving forward to example 1 and 2 back and forth. So in here, we are supposed to put the obstacle at the index 2. So it's mentioned with the red color in here. So moving on to the index 1, which is the type 2, and we want to put the size 3 at the index from 0 to 3. Let's consider we want to put the size 3. Let me draw the one side. Let's call like 1, 2, 3. I'm gonna put the background as a green color for here. Okay, this is terrible idea. Let me draw the proper number in here. Let's go, we have some valuation in here, and then we're gonna drop the number like 0, and I need to drop like this 1. I will remove it with this 2. Okay, I think that's more than enough. So we start from 0, which is going to be 1. This is going to be the 2. This is going to be the 3, 4, and 5, 6. Alright, cool. So from the index 0, we are supposed to put the blocker, which is placement here. Let's put with the red color since it is meant to be the blocking of the road. So block it, and I fill with this. So for the type 2, which is in the index 1, we want to put the size of 3. Let me draw the size of 3 in here. 1, 2, 3. I think we better use a green color for this. And then we have to put through from 0 to 3. So the range we can only consider is, there we go, 0 to 3. But let's say if we want to put in here, we cannot put it. The reason why we cannot put it is we have one blocker placement on the index 2. So that's why we retain the false in here. So let's move it on to the index 2, which is here. And we want to put the size of 1 from index 0 to 3. So we can put anywhere in here because size is only 1. And then we can simply return the true in index 1. How about the less index? So, which is the type 2, when you put the size 2, which is like this, from 0 to 2, then that definitely can put above and we can return the true. Because it is mentioned that we can touch the obstacle, we can intersect with any obstacle, but we cannot cross over the obstacle. So I hope you guys will understand the example 1. So it's also written that for the query 0, we have to place the obstacle at the x2. So a block size of the most 2 can be placed before the x3. So let's move on to the example 2. That will be a little bit challenging for us because I need to increment my valuation. So here is number 7. We got our 8. Yeah. So for the number example 2, we are given like type 1, which is put at the 7, and another is okay. Let's start with the index from gradually incremented. Now we are at the index 1, which is type 2. We want to put the size of 6. So 0 through 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay. And we want to put at the index of 7. So can we do it? Yes, because from 0 to 7, we still have one extra space and we can put anywhere in there. We can do it like that or do it like that. So that's why we return the true in here. After that, there is another obstacle come in. So we have to put the obstacle at 2. Then all of our requirement will change. Let's consider the index 4, index 1, 2, 3. Which is the size of 5, and we have to put from 0 to 7. But we can put it anymore. Oh, we still can put it because we still can touch the obstacle 2 and obstacle 7, and 1, 2, 3, 4, 5. So which is make us return the true in here. How about the size of 6? So definitely sure we cannot do it because it is blocking the 2 obstacle. So for each query, we can only consider the obstacle from the previous and we won't consider the other obstacle beforehand. So actually that is very difficult Leetcode problem I have ever seen in my life. You may think like I am over exaggeration of what I've stated before. We have solved around, like, according to my YouTube channel, that we have solved around like 80 Leetcode questions, and in my private Leetcode account, I have solved around 800 Leetcode questions. But if I have solved like a lot of hard questions, and we will see like this is very hard, and this one is extremely hard. And the reason why I'm saying extremely hard is we have to use the different type of data structure in here. If not, it's not going to solve it for sure. So for these, I have prepared a code snippet which is going to be useful for our Leetcode problem. But instead of writing that from the scratch, I will just copy paste it. And sorry about that, but I will try to explain what is the meaning of that data structure that I'm writing in here. So the first data structure I want to use in here is called segment tree. So what do I mean by segment tree? So it's just a tree that stores the cache information about the regions. So let's say we have a given array like do 5 3 7 8 do 5 3 7 and 1. Okay, just do the simple mathematical question. What is the maximum gap from index 0 to 4? So index 0 to 4 means we are selecting like index 1, 0, 1, 2, 3, 4. So we have to just find the maximum number, and the maximum number is 7. So by doing that, we are doing at the O of n operation because we're trying to scan it from 0 to n of the array, which is O of n. And I'm also writing down in here. So we are causing the solving the problem without using the segment tree. That way we end up with the O of n. So what about the maximum gap from 0 to 1 to 3? So what I mean by 1 to 3 is we're gonna narrow down through the 1, 2, and 3. That would be like that 5, 3, 7. So it's a 1 to 3. So we just scan through it and then return to 7 here. So I also have a visualization about how do we keep this kind of data in the tree in the proposition. What if we are expanding the tree gradually? What if I want to put the 1 just to keep track with our existing XML? I will put the 1 in here and 7 here. So that means I am recreating the tree by appending the number. Oh, that's so gross. The arrow. And I'm gonna change it to 1. So it will just stay 7 because we have to keep track of the 7 above of the tree. So if we check all the tree in here, we are using the maximum number as a root. So 3 and 7, 7 is greater than 3. So 2 and 5, 5 is greater than 2. So how about 5 and 7? 7 is greater than 5. How about 7 and 1? 7 is definitely greater than the 1. So that is what the segment tree comes in. So what about we want to check the maximum number of index 2 to 5? So that's come in like this. I'm gonna move this a little bit too easy to draw it, and then which is 0, 1, 2, 3, 4. And if we have to find the maximum from index 2 to 4, that would definitely easy return the 7. So the reason why we're using the segment tree is which will help us to segment the input into the partial scope, and then we have an index, so we can simply return this is the maximum number you can get it. How about other type, like instead of just a number, how about greatest common divisor? We can also use a segment tree to get the greatest common divisor of our array value. So that is the segment tree usage. Another one I would like to use in here is called Fenwick algorithm, which is also considered one of the tree. Okay, before moving on to the bandwidth algorithm, I will briefly explain about the different usage of the segment tree. So usually, if we declare the custom data structure, let's say we can use the tree by giving an input of array. Instead of giving an input array, we are gradually building the tree by using the original size of the tree count. So hope you guys understand the situation here. So you can see that it's gradually different with the original usage of the segment tree, but I will leave the theory of the segment tree in the description to save the time for it. And alright, I just paste the bandwidth algorithm. Okay, what is a bandwidth tree algorithm? It is considered the array which store the cache prefix information. What I mean by cache prefix information is, in our problem, we have an obstacle which is in the 2 and 7. What a bandwidth tree algorithm helps us is it will keep track of all the prefix number of the 2 and 7, and we can use it easily throughout the problem. So that is the bandwidth, and we can start working on our initial problem. So before we start, I'm gonna keep the values. Start with the 0, and what I want to do is I want to find the x maximum of our query. So let's consider query in queries. What I want to do is finding the max across the query, so which will be max x and q query of 1. So what I mean by query of 1, I am keep checking off this index 1 from across all the numbers, and I will also want to check if the query of type is 1, I will append it. If not, I don't need to keep in mind. So the reason why I'm using the value is just to create the obstacle across our problem by using the each index of 1. Alright, cool. That's for the query, and let's start with the limit of our problem. So for the limit, which is simply creating the extra room for our value, which I'm going to append to the limit in here. And then we need to keep track of the coordinate. Let's call coordinates, which is going to be the, originally it is supposed to be the values, but I want to keep the values unique, so I'm going to convert it into the set data type, but I still need to sort that unique number, so I'm going to put in the array and I'm going to sort that out. So yeah, that's a little bit technical, but if you keep solving this kind of problem, actually I spent around like 3 hours to fully understand the solution and question. So it took me like around 1 hour for the question and around 2 hours for the solution. And let's check the count of the coordinate, because we don't want to keep counting the coordinate across the problem. And then we're going to use a thing called hashmat, which is going to keep track of our indices in here. And for that, what I want to do is index and x will be our coordinate of enumeration. So by doing the enumeration, I can keep easily track of the should be the x, and that will be index. So every valuation have an index, so we can easily find which index is blocking across the problem. So that is still not the solution yet. That is just keep track of the index map. And then we can start with the bit, which is going to use the bandwidth algorithm, and then I'm going to pass the count, and then the same for the segment. Let's call seg. No, that's weird name. Segment. And I'm going to use segment tree in here directly. Let me check. It's a segment tree. Yeah. Tree and count. Alright, we got the segment tree, we got the bits, and we can start with the 0 index. Let's call 0 index, which is going to be the index map of 0. I believe the value will exist. Let me check the query. Okay, the query is minimum is 1, so we can use a force wrapping in here. The same for the limit index, which is going to use the index map of limit, and we have to do the force wrapping in here also. And then here is real of the problems come in. So we will have a boolean result array, and then I'm gonna iterate through the query in queries. So I want to start with if the query of type is 1. That is what we need to do for the obstacle. Let's call x and query of 1. So why naming the x? Because the question is keep using the x in across the question. So I'm using that as x for the query of 1. And we also need the index, which is going to be the, you can easily query it with the O of 1 using the index map with the force wrapping. And if we don't want to use, we can use the default value like 0, but I believe using the force wrapping is safe in here, but we can change the scope later. And we will do like, let's go before the count. What I mean by before count is before we count the fan width algorithm, I will put my x index to the fan width algorithm, and then for the previous index, that will be the bit of k index, which is written in here, and the k index will be the before count, and we need to keep track of the next interest, so which is going to be the bit of k of before count plus 1. Alright, cool. So we got what we did. So let's go. Previous will be the coordinates of previous index, and next will be the coordinates of next index. And so after we calculate our position and previous and next coordinates, we just need to add to our fan width algorithm by 1. So we have written here, so value of 1 that is going to add with our index, and we're gonna apply the segment tree in here using the update function that we copy paste before, which is the index of x minus previous and segment of, we can update the next index using the next minus x. Cool. So that is for plotting the blocker, which is query type 1. What about the query type 2? So that will be same. We're gonna need the query of 1, and but this time we also need the size, which is a query of 2. And in this case, there will be the different problem. Oh crap! I think I forgot to create the one helper function called upper bound, so which is going to help us, which is the upper limit of our given array in the limited scope using the segmented tree. And we have a target, which is going to be the integer, and we return the in here. So that's technically the binary tree problem. Let's use the right, left is 0. So as we know about the binary tree, right will be the array.count. Then we're gonna check like as long as left is less than the right, we can keep the loop running through, and we're gonna calculate the mid, which is going to be right minus okay, we can simply do like left plus right divided by 2, and if array of mid is less than equal to the target, what we're going to do is we're going to move the left to the mid plus 1. The same for the right. If right is in the target, we're going to move the mid to the right, and we can simply return the left index. So that is how we got. And then for the position, how we're going to do is we're going to calculate through the upper bound of our coordinate array and x and -1, because we don't calculate the maximum index in here. And then we also need to keep track of the obstacle count in here. The reason why we need obstacle count is we want to make sure that the obstacle that we have is not blocking in our way. So that's quite simple. We have an algorithm called Fenwick, which is going to pre-catch our previous number of the obstacle, and we're going to use that. So by summarization, not summarization, it's a sum of a position, and we can get the previous index, which is going to be the bit of k number of obstacle count, and we get our obstacle count, and we will calculate our previous, which is going to be the coordinates of the previous index. I think I make a variable round in here, should be the chord. Cool. And yeah, so we will check like before gap. Maybe best before is better. Best gap before. So what I mean by best gap before is before we plot in our placement of the block, we will check which one is the best place to keep it up. So we can use a segment tree in here by querying with the index of 0 and the previous index. And by doing that, we can calculate the partial gap, which is going to be the index that is from 0 through which kind of index we're going to do minus previous. So by that, we can append to the result by calculation of the maximum between the best gap before and partial gap. Right. And yeah, we need to compare with is greater than or equal to the size, because if it is not in between, we just return the false. And yeah, now finally return the result array. Not sure that will really work or not, because I copy paste half of the two algorithm absolutely in the line number 18. They're just going to be the chords. Queries. There's another problem in line number 48, which is going to be the position. There we go. I think it's a good sign. Nope. Holy cow, how can I make a lot of mistake of typo these days? Oh, crash. We have a runtime error. I think I make some mistake in somewhere else. Okay, let me check. The mid is correct, and oh, it's in the line number 38. I think there is something wrong with getting the next index. But next index is getting from the before count. That's true, nothing wrong. Right, let's try to debug it. Which should not be the real problem. So yeah, not sure what is wrong. Okay, let's check from the beginning. We properly set up the query. Maybe the size is wrong. That's what I was thinking. Yeah, if 1, if not, it is 2. But we are checking the 2 in here. 38. Where 38 is here. Let me think about it. Okay, did we update the segment before we start in the loop? That's my question. Absolutely. I think we need to do the some valuation, like adding the 0 index to our func with algorithm with the index of value of 1, and we also need to add the limit index. What should be the add? By adding the 1, and then also we do the segment.update. How do we update with the limit index and 0 index? Oh no, it should be the limit. Okay, let's try again. Ooh. Okay, I'm gonna scroll through for you guys to able to reference it. So this is the binary tree problem, just some portion of binary tree, and this is a func. But I will make sure I will drop the git snippet of the func and segment tree in the description. Okay, let's try to submit. It's such a long day already. Woohoo! We finally nailed it for 21 days without any break. And I believe that will be the O of Q log M, because we are using the same algorithm in here, the same for the O of M. And then it is mentioned that your complexity is optimal for the coordinate compression approach. Excellent work. That's a different output from comparison. And then it's mentioned that maintaining the dynamic gaps between obstacles using the segment tree for reach, maximum query, and func tree for order statistics. So that's what we really want to do. Alright, I really wish we don't face that problem in our interview because this one is extremely hard question that I have ever solved in my life. And hope you guys enjoyed the video, and see you in the next one. Bye.